this webinar, I will present the outcome of a geophysics study in the Yangibana region, Gascoyne Province, Western Australia. Integration of multiple geophysics methods were used to map the geometry of the Yangibana paleochannel that also represents the thickness of the cover, sequence or depth to the basement. Bilia is a network of cords going from one place to another, bringing life, giving water, feeding the land. In Noongar language and life, the word Bilia begins at Bili, meaning navel or belly button, becoming Bilia the cord of life. Without rivers, what would we have? As we rest beside it and ponder upon its continual nourishing, we connect deeper to our existence and the true meaning of Bilia. This is taken from Winmar and Bracknell 2021 Perth Festival booklet, explaining the importance of Bilia since our ancestor times, 40,000 years ago until today. The search for water is one that has defined human existence. Being able to map the geometry of paleo rivers, or usually termed paleochannels, and also estimate their depths is important for numerous reasons. In many terrains, the thickness of cover is defined by paleochannels, and the depth to economically important basement geology is a crucial surge that defines research prospectivity. Water sources are required for human habitation or agricultural needs. Paleochannels are a potential source of groundwater to meet these needs. Also, paleochannels can host mineral deposits such as potash and uranium. Purple outline in this image shows paleochannels or paleorivers on state scale. This webinar will focus on a localized area in the semi-desert Gascoyne Province, where understanding the geometry of paleochannels provides crucial information on potential groundwater resources, which can be the main sustainable water source in the region. The study area is outlined with this black and blue square. The study area is located in the Proterozoic Gascoyne Province. Outcropping basement is present only in the east part of the study area and is dominated by granitic rocks. In the central and west of the study area, the units of the Gascoyne Province are covered by Cenozoic alluvial units deposited by the Edmund River system. Most of the surface of the study area is covered by an alluvial unit of sand and gravel with ferruginous cement. Hastings Technology Metals Limited has done some drilling in the area, which is shown by these triangles, red and one yellow triangle. The drilling indicated the presence of an aquifer within the Yangibana paleochannel. Due to the limited drilling in the area, the geometry and depth of the channel were unknown. To understand the geometry of the Yangibana paleochannel and hence the likely extent of the aquifer, the Geological Survey of Western Australia carried out shallow passive seismic data acquisition in August 2018. The acquisition was designed on the basis of regional aeromagnetics, image shown in here, AEM data, which was also regional, and high-resolution gravity data, ground data, that was acquired by Hastings Metals. The other two datasets were acquired by GA and GSWA. The passive seismic traverses were chosen, as shown in this image, and there are 9 of them, and have been acquired by Trumino HVSR seismometers, shown here. What is a HVSR passive seismic? Over the next few slides, I'm going to show you how it works and how the data was acquired. HVSR is a horizontal to vertical spectral ratio method. It's a rapid and non-invasive technique. It doesn't require a controlled seismic source. The HVSR method records the ambient or natural noises in the subsurface at the broad range of frequencies from 0.1 to more than 2000 Hz. over the set time intervals, usually between 5 to 30 minutes, depending on the depth of interest. HVSR has two methods, single stations and array-based. HVSR, or horizontal to vertical spatial ratio method, uses Nakamura technique that uses three-component measurements: X component, or north-south, Y, east-west, and the Z component, which is the down or depth component, of ambient noise, as a seismic source to determine and evaluate fundamental seismic resonance frequency. The time series data recorded by terminals are transferred into frequency spectra by fast Fourier transform. Horizontal components are usually very similar, unless there is a strong anisotropy in the near surface. Vertical component dips where resonance occurs from trapping by underlying layers. The HVSR method is based on a simple two-layer system, such as regolith overlying bedrock. The resonance frequency is amplified with a stronger and sharper impedance contrast between the two units. So that is the impedance contrast between units. The impedance contrast results from the different shear wave velocities of the two layers and their respective densities, Vs1 and Vs2. The shear wave velocity is a measure of how fast the ambient noise travels through a rock unit. For example, a shear wave velocity of clay and sands is an average about 200 meters per second, while shear wave velocity of granitic rocks is more than 750 meters per second. Hence, a very strong impedance contrast is usually observed at the regolith bedrock boundary due to the vastly different properties. The greater the difference in shear wave velocity between the two units, the larger the impedance contrast and the greater the resonance frequency peak in HVSR. The resonance frequency at which the impedance contrast is measured is a function of the depth of the boundary between the two units. This relationship between frequency, shear wave velocity, and the depth is the fundamental for short station passive seismic approach. And this is the equation that we will use through this study. Multiple frequency peaks are possible contrast between layers, and the peak will occur at the resonant frequency corresponding to each subsequent layer. If we have very shallow silt gravel in, let's say, 10 meters, it will be picked up at the high frequencies. Then as we go deeper into sandstones, it will be picked up at the lower frequencies, and bedrock usually, the deeper we go, the lower the frequencies are. So the deep bedrocks will be picked up at the frequencies less than 1 Hz. Terrain was mostly clear of vegetation with sandy to piezolytic ground. To ensure good coupling, 3 different spikes were used depending on the ground conditions. Short spikes were used where the ground was very hard and cemented, so we were not able to penetrate the spikes into the ground. Custom-made spikes were our preferable method and were used where the conditions were right or the ground was softer. Long spikes were used where there were a lot of piezolites in the ground and a lot of cementation, so basically or practically where it was too hard to penetrate the custom-made spikes into the ground. The Yangibana paleochannel is located within the limits of the regional 2013 Capricorn Tempest AEM survey. The survey was conducted as part of the Western Australian Exploration Incentive Scheme and managed by Geoscience Australia on behalf of the GSWA. 30,119 line kilometers in total were flown on a 5,000-meter line spacing over 60 flights. This red area shows the total Capricorn Tempest AM survey. Red lines are the lines in the study area. Only these two lines actually cover our study area, and those are the lines that we have then additionally inverted by Intrepid Geophysics using a 2.5D inversion method. The data for both the entire 2013 Capricorn Tempest AM as well as the inversion 2.5D inversion of these two lines, line 2501 and 2601, are available through GSWA Data and Software Center. The background image is a high-resolution Bourget gravity data acquired by Hastings Technology Metals. The blue dots are the 17 traverses that have been used to acquire this data and on a 100-meter station spacing. Over the next few slides, I'm going to talk about data analysis and the results of the HVSR passive seismic acquisition of the 9 traverses that we've done, and how they compare to the 2.5D inversions of AM lines, the regional lines, as well as the high-resolution Bourget gravity that has been done by the Hastings. After downloading the data using Moho's proprietary Gorilla software, Moho is the company that also produces and sells Tremino seismometers, the individual measurements were selected for analysis. It was observed that the recordings from the deepest part of the paleochannel had the most distinct HVSR peaks. The recording shows an acquired HVSR spectral ratio, which is this red line, and the 95% confidence limits, which are the two gray lines. The stratigraphic peak occurs at 0.94 Hz, which, being lower than 1 Hz, indicates an impedance contrast at depth rather than a shallow regulated interface or cultural noise. The amplitude spectrum of the 3 components was computed for each 20-second window via fast Fourier transform and smoothed a triangular 10% window. Horizontal components, north-south and east-west, in the amplitude spectra are usually very similar unless there is a strong anisotropy in the subsurface or near surface. The vertical purple component dips due to the resonance from trapping by underlying layers, creating an eye-like shape in the amplitude spectrum. This eye-like shape in the amplitude spectrum corresponds to the stratigraphic peak in the HVSR. The consistency of the noise signal through the acquisition is shown in the time stability plot. A linear feature in the stability plot represents a constant, coherent noise occurring at the same frequency as the eye-like shape in the amplitude spectrum and the stratigraphy peak in the HVSR. And in here we refer to it as a normal trend. After data cleaning and processing, the interpretation of HVSR measurements using Gorilla software involves fitting a synthetic curve to the measured frequency peaks in the HVSR spectrum. This was carried out by constraining a velocity depth model using the frequency equation and the HVSR reading at the drill hole that was positioned in one of these HVSR transects and that reached the basement. The modeled velocity of 290 meters was used at each subsequent HVSR measurement to estimate the depth to the basement, that is, the depth of the Yangibana paleochannel. A limitation of this study is that the shear wave velocity of the regolith package has only been calculated at one location. The use of this constant velocity throughout the study area is a simplification, but without more basement intersecting holes, this is unavoidable. To visualize HVSR data, the values have been normalized using this equation, minimum and maximum normalization displayed here. Now, normalization transforms the HVSR amplitudes, which can vary a lot between sites to range between 0 and 1. This makes the HVSR values comparable between sites, although in some cases enhances noise. Here is an example of normalized HVSR values. The frequencies were then converted to thickness, assuming a velocity of 290 meters per second and using the frequency equation. The thickness was then subtracted from the elevation of the site to give the depth of the data point, which are these black rectangles, which also are showing the depth to the basement. Same normalization method has been applied to all 9 traverses in the study area. And the data was imported into a 3D surface to create a 3D geometry of the Yangibana paleochannel as shown in here. Due to the large distances between profiles 5 and 9, compared to other profiles, the dataset was interpolated in 2 parts. As an alternative, several artificial data points were added between profiles 5 and 9, where no data were available, and the dataset was interpolated to produce one surface representing the base of the paleochannel. How do these results compare to other geophysical methods? Let's start first with AEM. Here we have 2 AEM lines that we've done 2.5D inversion, 2501 and 2601. Along 2501 line, we have 2 traverses, traverse 3 and traverse 5, HVSR traverses. And along 2601 line, we have traverse 7. Interpreted base depths of the paleochannel from traverses 3 and 5 along AM line 2501 clearly distinguish its geometry from the conductive regolith layer. The passive seismic traverses do not extend across the entire conductive anomaly. Nevertheless, the passive seismic results immediately before the gap in the data still suggest that the base of the channels. This suggests that this middle conductive anomaly in AEM is representative of transported regolith unit. Comparison of the passive seismic and AEM data along traverse 7 shows that the depth to the basement calculated from HVSR data is broadly similar to the depth to the basement from AEM. However, one of the major differences is the maximum depth of the paleochannel. Passive seismic permits a shallower maximum than AEM. This may be a result of the inversion algorithm used may also represent an overestimation of the depth due to challenges in recovering the conductivity of the layer beneath the conductive regolith layer overlying the paleochannel. Also, it can be due to the only single velocity constraint from one drill hole to estimate the paleochannel depth from the HVSR. HVSR traverses 1, 2, and 12 follow parts of 3 gravity profiles. HVSR traverses are indicated by black line, gravity profiles by blue lines. Along these profiles, the depth to basement values calculated from HVSR data, which are the empty black circles, have been compared to Bourget gravity data, which are the red crosses, and the black solid circles are topography. High-resolution Bourget gravity data shows the paleochannel as a gravity low, produced by an increased thickness of low-density channel film. A similar geometry to the depth of the basement of the paleochannel is seen between the HVSR and gravity profiles. The HVSR data are generally more scattered than the Bourget gravity data, particularly at the southeastern part of the profiles 1, 2, and 12 as shown by these circles, where measurements were made about shallow bedrock. To conclude, the three geophysics methods used in this study complement each other in mapping the geometry of the paleochannel. Depending on the scale and the budget, each method can be used individually in paleochannel mapping. For example, AEM, regional AEM, is better for large-scale paleochannel mapping, while HVSR and gravity would be better for smaller-scale mapping. However, when integrated together, these three methods, a more detailed and robust model is produced. The published version of this study can be downloaded from Geological Survey of Western Australia e-bookshop. Thank you.